Thank you for the introduction. So this talk is going to be in many ways about a classic Web 2 question, a pure parallel execution problem. And this is jointly with colleagues at University of Southern California and Supra Research. So, just to sort of revisit an elementary, model of blockchain. So you have a set of transactions form a batch, and at some point, a batch gets added to a validator node. And this is a very deterministic thing, typically in today's blockchain ecosystem, where a validator node receives a block of transactions and it tries to execute that block of transactions. For most parts, historically, this has been a sequential execution process where, one transaction gets executed and then the next one starts, finishes executing. This way you get determinism. So at the end of that execution, all validators reach the same state after executing that same block of transactions, which is great, except if your validator node is, a fancy AMD EPYC with 48 cores, you're pretty much running a single threaded execution, which makes absolutely no sense. And, this has sort of become a bottleneck for most parts. And so there's a considerable amount of work recently that's starting to look at parallel execution of blockchains. And this talk is purely about parallel execution of blockchains. So for all practical purposes, a transaction is just simple, coin transfer, an arbitrary smart contract, anything that you can imagine that is trying to get executed. So the question we are asking in this talk is, okay, given a block of transactions, how do we execute it in the most efficient way? Now the execution must be safe. So safe in the sense, the way we determine safety in a deterministic execution. It must maximize CPU utilization and minimize the amount of memory footprint that you're trying to use out of it. Which sounds like a standard problem, right? This is something that people have studied in databases and parallel systems for 30 plus years. Except what makes it fundamentally different in the Web3 setting as opposed to the classic Web2 setting is the fact that the transactions in this model that we are talking about must be executed in parallel, but the conflicting transactions must respect a preset order, this order that is given by the block proposer to the set of validators that is required for determinism. Now, there are other models that exist, and I'll sort of allude to them later in the talk, but this is the most prevalent model where, a block proposer gives you the block and a preset order in which you're trying to execute those transactions, and you're trying to respect that order as part of your execution. So the need of the hour is, how do I resolve transactional conflicts in a block and maximize parallel execution throughput? Now, conflict, for any of us who sort of obviously know this, is to talk about state dependency. So in our case, we care about write-write dependency and read-write dependencies, the so-called happens before relation in distributed computing. And I have this notion of a preset order, which is a canonical transaction order, which is defined by the block proposer. Obviously, non-conflicting transactions can be executed in any order because they sort of contribute to an equivalent total order. And the conflicting transactions must respect the order of transactions in the block. So why is this a problem? Why is, dealing with conflict dependency a problem? This is your classic example, right? So imagine if you just have, a basic bank account or something, and two people who have access to that bank account are trying to withdraw concurrently from that same account. If you just have $100 in your account, and if two people are trying to withdraw $100 at the same time, oblivious of each other, obviously only one of those transactions can succeed because there's a read-write dependency on it. And this is something that we want to avoid, obviously, because you're then in an inconsistent state. So a transaction is something that is a sequence of reads and writes that are performed to a set of smart contract locations. Now, this depends on the memory model, obviously, of the individual virtual machine. Ethereum is very different from Solana, which is very different from Move. But for simplicity of sort of visualization of this problem, let's just look at transaction as a sequence of reads and writes. So here I just have two transactions, T1 and T2. Transaction T1 is reading to a memory location x1, and let's say it's returning the initial value of that location, which is 0. Transaction T2 comes in and is trying to perform a read of a memory location x2 and is also returning the initial value of that memory location. Transaction T2 is now writing to this memory location x1 and writing this new value, which is not being seen by transaction T1. And Now I have transaction T1, which is also attempting to write, this time to a memory location X2, which is concurrently being read by transaction T2. Transaction T2 goes ahead and commits. Now we are in an asynchronous environment, so there is no concept of time. There's only causality, right? So we only know when something is changed, when the memory state of the system evolves. So, transaction T2, which is executed by another thread, goes ahead and executes and completes the transaction. Now at this point, transaction T1, there is no way to justify the state read by transaction T1 because I have to respect the preset order, in this case T1 and T2. So if I assume transaction T1 finishes first and then transaction T2 comes, then transaction T2, the value of X2 that was read by transaction T2 should have been 1 because it should have seen the state read by transaction T1, which is not the case here because of this interleaving that happens. So this is an unsafe execution that we would want to avoid. Now the other option would be to say, okay, I could re-execute transaction T1. Okay, I could try and re-execute transaction T1. I again, read X1 0, and then I write X1, write 1 to memory location X2. And again, this also does not work because, I cannot justify in any case, even if transaction T1 re-executes, the value read by transaction T2 of the memory location X2. So what we're really trying to understand is what are the fundamental limits of what needs to be done in order to get parallel execution to be provably safe. So in this example, the only real scenario that seems to work is for transaction T2 to wait until transaction T1 goes ahead and commits its state to shared memory. So if transaction T2 waits until T1 goes ahead and commits its state to shared memory, then I'm allowed transaction T2 is actually going to see the value committed to shared memory by transaction T1. So the read of X2 is actually going to see the value 1 that was written by transaction T1. Make sense? So the resulting serialization is preset order preserved, and this is a safe execution that we can work with. Now, with block transactional memory, unlike those of you who are familiar with sort of traditional transactions and things like that, so we expect this preset order to be respected, which is a safe execution. And if it's not respected, we refer to it as an unsafe execution. Now, with traditional transactional execution, we would say, okay, the execution, as long as it is equivalent to some sequential order, that is great. But in block transactional execution in the Web3 world, we look for a sequential execution that is equivalent to exactly this one preset order. And that makes the problem fundamentally different. It's almost like an ordering curse that you'll have to overcome. So in terms of, and let's look at another example to motivate sort of where we're getting to in terms of the contribution in this work. So here I have a transaction T1, which is reading a memory location X1, and a concurrent writer, which is writing 1 to location X1, and which is also writing 1 to a location X2. And then I have transaction T1, which is trying to perform a read of this location X2. Now this read is going to return the value 1. So now I get this old new inversion. So transaction T1, the memory location X1 misses the write performed by transaction T2. The read of the memory location X2 gets the value of the write performed by transaction T2, which again is something that cannot be justified. This read is not legal. So this cannot happen in any sequential execution of these two transactions, which respects the preset order. So the question we are asking is, okay, this sounds like a scenario where if transaction T1 had information about the fact that there was a dependency with transaction T2, I could have avoided this scenario. I could have avoided this scenario simply by having transaction T1 be aware of the fact that transaction T2 is going to perform a concurrent write. I could have kept additional state of all the versions that exist, and I could have had transaction T2, when it performs the read of X2, just simply return the initial value, because that would perfectly justify the legality of the read. So if I had prior information of this transaction dependency order, in this case, the fact that T1 is dependent on T2, then transaction T1 would simply return the value 0 for the read of X2. So it would basically leverage using some sort of a multi-version data structure, and this prior knowledge would allow it to execute. So the two transactions would execute concurrently, essentially preventing transaction T2 from having to wait for transaction T1 to complete. So just to sort of give a mental model, so this is, this is pretty much the state here. So if you have a largely sequential execution, you of course get no concurrency, you get a limited throughput. If you have a fully parallel execution, which is oblivious of dependency, the execution could be unsafe. And so we are in the sort of preset parallel world, which provides some notion of a bounded concurrency because you're essentially constrained by these conflict chains that exist. The fact that these conflict chains you're not aware of. So in this example, so if I have 6 transactions here, T2, T3, and T4 are dependent on each other, T5 and T6 are dependent on each other. So I get these like little cliques of conflict chains, which if I had prior information about, I could leverage this for better parallel execution techniques. Which again is not, which is seemingly an obvious observation to make, but the question is how do we sort of build these conflict chains, how do we construct these dependencies, and then how could we actually leverage it for faster parallel execution. So just sort of a bit of a background, right? In the taxonomization of the parallel execution world comes, broadly speaking, in 2 models. One is sort of what I would like to call the read-write-aware execution model, which is where either the transaction data sets are provided a priori as part of the entire blockchain's ecosystem consensus process, or the read-write oblivious model where this information is not available and you're just trying to execute based on the preset order at the validator node. And most blockchains, it's fair to say, sort of fall within one or the other model in some sense. The most famous example for the read-write-aware model is probably Solana, which gives you the entire read and write set as part of its execution, and pretty much Ethereum and all, and Aptos Move sort of fall under the oblivious category. So the question we, in some sense, are trying to understand is, okay, so the read-write-aware model, has some benefits. You could leverage it for possibly faster parallel execution. The read-write-oblivious model does not give you any of this access set information, and you're essentially running blind and trying to get the best possible performance subject to the ordering curse. Can we do something which is just right Goldilocks, right? Something that where you can learn with some best effort information, some transaction dependency information, and yet get the benefits of the read-write-aware model, which would probably give you the full conflict information and the transaction dependency information. And that's really the main contribution of this work, where we present a family of algorithms which are, as I said, somewhere between the read-write-aware and the read-write-oblivious model, with some best effort construction of transaction dependency sets at the validator node using very lightweight static analysis. We create these conflict dependency sets to identify transactions that definitely do not conflict. So the insight here is what matters more is knowing 2 transactions definitely do not conflict. I don't care about the transactions that even may conflict. That's fine. So I'm trying to do something very best effort here. And then the algorithm leverages a custom scheduler in order to execute these transactions with as much parallelism as possible. Our primary goal here being to minimize the number of validations of transactions. So, one of the main 2 main bottlenecks in parallel execution. One is having to validate whether the values that you've read before are still consistent when you get to the end of the transaction, and minimizing the number of re-executions. And with that in mind, we build a family of algorithms that leverage proactive conflict prevention and some form of adaptive execution, essentially trying to minimize the need for costly re-executions and transaction reset validations. So we built a large data set, which is from historical Ethereum mainnet blocks. I'm going to talk here about, the theory of it is sort of very general and very abstract. I'm going to just talk about some high-level results that we derived for the EVM implementation, where we built a full-blown conflict analyzer in order to construct these transaction dependency sets, and built a custom implementation which leverages this conflict analyzer for faster parallel execution. We built this as a Rust implementation on top of the parallel EVM chain data structures, and a custom implementation of a conflict analyzer with a restricted set of Ethereum contracts in mind. Now, there are more interesting things that we've done with the conflict analyzer that allows us to build this, rigorously for all classes of Ethereum contracts, but that is something that is significantly more costly, and it's not something I'm going to talk about much in this talk. The experiments are conducted on a single socket AMD machine standard AMD EPYC machine. One important thing for the purposes of this talk, we're not sort of worrying about the latency of accessing state from persistent storage and things like that. So everything is sort of assumed to be in memory. We sort of take the pre-state, we load it in memory, and that way we sort of just clearly understand the benefits that are coming from parallel execution. And so here the graphs show the relationship between varying threads on varying conflicts with an alpha tail distribution factor within a block. And we look at the throughput through the histograms and the execution latency as line graphs on the secondary y-axis. So the main takeaway here is that we typically see, especially on synthetic workloads, where we can sort of play around with different conflict distributions and ratios, we do see consistently 3x or more performance, and in many workloads we even see up to 7x performance improvement over sequential execution, which is nice. But then again, one thing to remember is that all of these benefits sort of come through only at higher thread count, only when sort of block sizes are significantly big. So what happens is when you have like really small historical blocks, as you see on the left here, which is a block size of 77, you don't see any real performance of performance benefits coming from parallel execution. And this is probably true of any parallel execution algorithm. But we do see, as the sort of block sizes increases, the conflict ratio increases, and as the thread count increases, we do see some non-trivial performance improvements over the sequential execution. We also see one of the other things is, significant stability even in high conflict DeFi workloads. And this is good because one of the things that happens is when there are significant number of conflicts, sometimes you see this like big difference in performance between the high conflict workload and the low conflict workload, which significantly affects your CPU utilization. And that is something which is a significant factor in lots of falls that happen at the validator nodes. The other aspect of our algorithm is the fact that it's actually an adaptive algorithm. The fact that we are able to pre-compute this conflict threshold allows us to dynamically choose between our family of algorithms, including one class of algorithms, which is a DAG-based, largely serialized algorithm catering to high conflict workloads. And here what you see is that even by having to pre-compute this conflict threshold, it does not impose a significantly high overhead over the nature of your parallel execution algorithm. I'll just conclude this talk by saying that in many ways, the parallel execution world in the smart contract ecosystem has been caught up in the read-write oblivious versus read-write aware debate. But there is a world in between, and that world can be leveraged for several aspects of it. There are deep implications for it, even in terms of MEV mitigation. There are even proposals right now to go beyond all of this in order to prepare a block directly at the mempool level, which is largely conflict-free, which allows for faster execution. It introduces the possibility of more non-deterministic approaches, and hopefully, this work sort of brings about more contribution in that space. And with that, I'll stop. And there's apart from the paper which I mentioned right now here at AFT, there are a couple of other papers which more conduct historical and theoretical studies on the nature of conflict workloads and parallel execution ecosystems. Thank you.
Thank you. I think we have time for one quick question.
Hi, great talk. My question is regarding how granular should the dependency detection be? Let's say maybe I deploy some contract, and in one memory location, instead of using two memory locations for two variables, I just split it, you use bits as information. Do you think but one transaction uses just one bit and another other bit? Do you think the detection should be that granular, or do you think something like this should be handled by making changes to the compiler such that something like this doesn't go on chain?
Thank you. So, I mean, the obvious answer I'm going to give is yes, it helps to have the detection as granular as possible because that sort of gives you a more fine-grained characterization of transaction dependencies. Right now, with sort of the current I mean, at least, with every memory model is different, but at least for EVM, it turns out that even sort of being able to do this simply by looking at sender-receiver addresses, simply by looking at ERC20 contracts, you are getting significant benefits. But once people start deploying, more complex, smart contracts and more complex DApps, you know, I mean, we do. It turns out we do need like sort of a bytecode decompilation techniques, and then things like that in full-blown static analysis techniques in order to get more fine-grained information, which turns out to be a little bit more costly, because then if you add that up along with the cost of actual parallel execution, then you sort of lose the benefits that you would want from parallel execution. So in that case, you would probably go to some sort of offline model where you would probably pre-compute it, keep that information available, and then use it at runtime just at the point in which the validator nodes are trying to execute. So if you're able to do that, that would be of sort of significant benefit. In terms of compiler level changes, I mean, yes, I mean, there are obviously benefits to make, but again, it's a question of trade-off in terms of how much work you would do in order to get, how much the kind of performance benefits that you're looking for. But as I said, even with this, we already see close to 5x consistently on most workloads.
Okay, thank you.
Great. Let's thank our speaker again.
Thank you.